Hi, I'm Norman Wildberger. Today we're going to have a look at the dodecahedron and its symmetry from the point of view of looking inside the dodecahedron for some canonical structures. I'm going to leave the dual object, the icosahedron, to you to investigate. So our dodecahedron, classical subject, one of the most beautiful mathematical objects in the entire spectrum of the subject, revered since antiquity. Here it is here, and perhaps if you look at it from about there, then you see some picture like this. So it has 20 vertices, it has 30 edges, and it has 12 faces. Now this solid does not have twofold or threefold or fourfold symmetry. We've seen those kinds of symmetries for the tetrahedron and the cube and the octahedron. The dodecahedron and the icosahedron instead has fivefold and sixfold symmetry. And that's going to be sort of the heart of the topic today. We're going to look to see how this fivefold and sixfold symmetry are revealed or reflected in internal structures within the dodecahedron. So I'd like to frame the fivefold symmetry of the dodecahedron into things I call handle sets. So let's have a look at the 5 handle sets of the dodecahedron. Okay, there are 30 edges, and these 30 edges form 15 pairs of opposite edges because the dodecahedron is symmetric through its center. In fact, all of the Platonic solids are except for the tetrahedron. So here's an edge, and here is the opposite edge down here. These form a pair of opposite edges, and so there are then 15 such pairs of opposite edges. Now it turns out that these 15 pairs of opposite edges form 5 groups of 3 pairs, which have a particular configuration with respect to each other. These 3 pairs are in mutually perpendicular directions and form what I call a handle set. So, for example, in this representation here, the pair of this edge and this edge, that's one pair of opposite edges, and then there's this pair over here, it's another pair of opposite edges, and then there's this pair up here, another pair of opposite edges. And they are all in mutually perpendicular directions. I can show it to you better, I think, perhaps with this thing here. So we'll put this thing here so that this edge down here is supposed to be this one here. Okay, so what are we talking about here? We're talking about this pair of edges as like a handle. Okay, that's a handle. Now, associated to that handle is also this pair. This direction of this edge is perpendicular to the direction of edge of the one that we started with. And then along with that, there's also this pair of opposite edges. Okay, so there's this pair of opposite edges and this pair as well as this pair. They're kind of symmetrically placed around the dodecahedron. And these 3 pairs of opposite edges together I call a handle set. So that's what the handle set is. It's this triple of opposite pairs of edges. Now every edge is in exactly one handle set because a handle set is determined by an edge. So we can see the relationship between the edges in the handle set as follows. If we choose this edge here to start with, okay, then this edge has 2 edges emanating from it on this side and 2 edges emanating from it on this side. So if we look at the 2 edges emanating on this side, that's part of another face, and the other edge that appears in the handle set is opposite to this vertex in that adjacent face. So similarly, the end here is part of a pentagonal face, and the edge that's sort of opposite that vertex in that pentagonal face, it forms another element of the handle set. And that carries on for the other ones. For example, if you look at the end of this one here, then there's 2 emanating that determines a pentagon, and then the opposite edge to this vertex in that pentagon is this edge up here. Okay? So it's all symmetric and all of the edges in a handle set have the same relation with each other. Every handle set, of course, involves 12 vertices, because we have 6 edges, and each edge has 2 vertices, so altogether 12 vertices. Now, it's more usual in the literature to consider, instead of handle sets, cubes. So there are also 5 cubes inside the dodecahedron. And it turns out that associated to each of the 5 handle sets, there is a cube. And that's formed by the 20 minus 12, or 8 vertices, which are not involved in the handle set. So there are 20 vertices altogether. 12 are involved in any one handle set, and that leaves 8 vertices left over for every handle set, and that is then turning out to be a cube. And let's have a look at what that actually looks like. So here's a picture, okay, of the same story here, and let's look at the handle set consisting of this edge together with its opposite, together with this edge and its opposite, and this edge and its opposite. Okay? Now, which vertices are not involved in those 6 edges? Well, the vertices that are not involved are this one, this one, this one, and this one. They form the top face of a cube, together with this one, this one, this one, and this one, forming the bottom face of a cube. So here, if we just return to this picture, so the red handle set was this edge, this edge, this edge, this edge, that one, and that one. And here are the 8 vertices not involved in that handle set, and they form a nice little cube. And you can think about the relationship of the cube with the handle set as being particularly instructive. So, for example, if we think about a cube like this, then the relationship of the handle set is that it's something like this, that over here, somewhere around about there, is one edge of the handle set, and then over here is another edge. Then there's another edge here, and another edge here, another edge here, another edge here. So we can kind of imagine the handle set as being almost handles on a cube. Okay, so each edge of the handle set has 4 vertices adjacent to its endpoints. So here's another way of thinking about how to get that cube. If we start with, say, one edge, let's say the top one here. Okay, so there are then 2 vertices here, and there are 2 edges coming from each of these vertices determined by that particular edge. Right. So this one edge determines sort of 4 adjacent vertices, and they are the vertices that form the face of a cube. So to every edge, there's this square of the sort of the nearest vertices to that edge. That's really all that's happening here. We have 6 of these handle sets. They determine these 6 square faces of the cube. And so there are then these 5 cubes in the dodecahedron. 1 for each of the handle sets. So each of the 5 cubes has the center of the dodecahedron. They're all actually completely centered inside the dodecahedron. And an edge of such a cube is a diagonal of a pentagonal face of the dodecahedron. So we said that the faces of these cubes consist of things like this. We're joining this point to this point to this point to this point to this point. Right, so the actual edges of the cube are actually diagonals of the pentagonal faces. Okay, so there's a pentagon face. It has these as the edges, and then these are diagonals. It has these 5 diagonals. And those are the edges of the cube. So as a little exercise, show that each vertex of the dodecahedron actually belongs to 2 cubes. hope that makes sense numerically, because the cube has 8 vertices. So there's 5 cubes, that's 5 times 8 vertices altogether, that's 40 vertices. But the dodecahedron itself has 20 vertices, so that makes sense that every vertex belongs to 2 cubes. Just convince yourself of that. Now let's have a look at what happens if we look at not just one handle set, but a pair of handle sets. So we might be interested in what's the relationship between 2 different handle sets. Let's first of all make the observation that if, say, we're looking at a red handle set to begin with, there's the red handle set, that any other edge is adjacent to exactly one of the red edges. So if we pick any other edge, for example that one there, then that's adjacent to exactly this red edge. Or if we choose that edge there, that's adjacent to this one. Or if we choose that edge there, that's adjacent to this one. Right. So every edge is adjacent to a red edge. That means that any 2 handle sets really have the same relation because they're determined by a pair of adjacent edges. For example, the red and the green handle sets are determined entirely by this pair of adjacent edges, a red one and a green one. So you specify any pair of adjacent edges, call one of them red, the other one green, they determine 2 handle sets. And any 2 handle sets are determined by such a pair of adjacent edges. As a little exercise, show that a pair of handle sets, for example this one, a red and a green handle set, determines a subdivision of the faces into 2 subsets of 6 each. That there is then a natural way of subdividing the faces into 2 different types with respect to these red and green handle sets. And each of those 2 subsets has 6 faces in it. And you might just like to compute how many different pairs of handle sets are there. These cubes and handle sets inside the dodecahedron can also be an aid for us in visualizing and even constructing the dodecahedron. So for example, if we wanted to construct a dodecahedron, one way would be to start with a cube. Of course, very easy to make. And then just attach handles to each of the faces. But we have to do it in the right way. So we'll put handle here for this face and here for this face. And then here and here for those faces. And then here and here for the top and bottom. And we have to position these handles in just the right way so that basically we're forming a pentagonal shape. So we end up having that this is a pentagon, a regular pentagon, with this as a diagonal. So if we start off with a diagonal, then we have to basically compute the side of a pentagon, and then we have 3 equal sides. These are going to be 3 equal sides of the regular pentagon forming part of the pentagon, and here's the rest of it. And so that's one way of thinking about it. We're attaching pentagons to these edges in such a way that they kind of match up. So we could say that the dodecahedron is composed of the cube plus its associated handle set. We're getting 8 vertices for the cube and another 12 for the associated handle set. It's kind of a decomposition of the dodecahedron. That might be useful if you actually have to make one. From the 5 cubes of a dodecahedron, we can go one step further and deduce that a dodecahedron has 10 tetrahedra. So since each of the 5 cubes of the dodecahedron determines 2 tetrahedra, there will be 10 tetrahedra in the dodecahedron. I remind you that if we have a cube, that we saw that it had a 2-fold symmetry. There were 2 tetrahedra associated to it. For example, we could take the bottom 2 there and the top 2 there. Right, those 4 make a tetrahedron. And then the other 4 vertices, which are these 2 and these 2, they also form a tetrahedron. So we have 2 tetrahedra forming a cube. Right, so we have altogether 10 tetrahedra inside this dodecahedron. So for example, here's our dodecahedron, and in the large black vertices here, they form a cube. So there, and there, and there, and there, and there, that was a cube. And then inside that cube, if we take every sort of second vertex, we get, for example, this tetrahedron. If we look at the relationship between any two of the vertices of that tetrahedron, we're seeing that they're connected or separated by some kind of a zigzag path, sort of like a Z kind of shaped path. So for example, to go from here to here, right, we could get there by going from here to here, and then from here to here, and then from here to here. So when we're going from here to here, we're just going along one edge, and then we have a choice of two. We can either go left or right. So we decide to go left, sort of around this face. And then when we're at that point there, well, we could keep going left, which would be to carry on going around that same face, but we don't want to do that. We want to go to the other face. So we turn right instead to go onto this face here. So we're kind of making a left turn and then a right turn, and that gets us from one vertex to another. So there's a simplified picture. Starting from here to going from there, we're making, in this case, a right turn and then a left turn. So going around a little bit of one pentagon and then around a little bit of the next pentagon. Altogether a Z shape, and that takes us from one vertex to another. So there are 10 such tetrahedra inside the dodecahedron. So we have 10 tetrahedra inside the dodecahedron. Now we can take those 10 tetrahedra and we can decompose the dodecahedron into actually 5 of them, because we have 4 vertices to a tetrahedron, so 4 times 5 makes 20. So here's how to partition our dodecahedron into 5 tetrahedra. And I'm going to show it to you with a graphical model, illustrating that you don't always have to have this geometrically sort of valid representation. For a lot of purposes, a graphical model suffices, because we can still see where the faces are. Okay? So this is still a pentagonal face. This is a pentagonal face, and we have to remember that the outside now is also representing a pentagonal face. So a green tetrahedron, there, 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 and there. So notice to go from here to here is a Z path. So we're going here, and then here, and then here. So we're going a little ways along that face, and then we change to go around the adjacent face here. And any two of those 4 green vertices can be connected in such a way. So for example, to get from here to here, there's exactly one such Z path. We can go from here to here to here to here. This is a path around the outside face, and then from here to here we're then switching to going around this adjacent face. Still a Z path in the same sense combinatorially. Okay, and once we have the green one, well, then we can sort of rotate it around, because just a rotation about the central point will just rotate everything around. And so there's then a red tetrahedron with little red circles, and then a black one, and then a blue one with squares, that one there, there, and there, and then one more, this triangular red one with vertices here, 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 and here. And you might like to play around, just draw yourself a more accurate geometrical representation of the dodecahedron and draw in those 5 tetrahedra. Or if you actually have a model like this, you might actually get some string or elastic bands or something and actually construct your 5 tetrahedron inside the thing. Pleasant exercise. So that's been quite a lot about the 5-fold symmetry of the dodecahedron. There is, of course, also this 6-fold symmetry, and that's a lot more obvious. And that's really just because there are 12 faces, and the 12 faces come in opposite pairs. And so there are 6 pairs of opposite faces. And if we want to have some geometrical objects that really capture that, we can do the same kind of thing that we did for the cube. We can just take the line segments that join opposite faces. They are then going to be diameters of the dodecahedron. We can call them face diameters, the same way that we did for the cube. So they're then these 6 face diameters joining centers of opposite faces. And any 2 of them pass through adjacent faces. So you can sort of have a look and see, convince yourself that if you take any 2, say that one and maybe this one, that they are passing through adjacent faces. Or this one here is also adjacent faces, in this case this face and this face. And here's sort of what some of them look like, just 2 of them, some adjacent faces. Okay, if we have these 6 face diameters, any 2 of them have the same relation from this observation. What about 3 of them? So here's an exercise. Show that triples of face diameters, in this sense, are basically of 2 different types. That if we choose 3 different face diameters, there's 2 possible configurations that those 3 diameters can form. And then there are 10 of each type. So we get another kind of 10-fold symmetry from the kinds of triples of face diameters that we can create. So those are some interesting internal symmetries. But there's another aspect of these sort of internal combinatorial symmetries that I want to tell you about. And those are sort of remarkable polygonal paths that arise on a polyhedron that named after Petri. So they're called Petri polygons. And so we're going to talk about Petri polygons, not just for the dodecahedron, but for all of the platonic solids in our next video. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.